Hi everyone, this is part 2 of our material on linear codes. So before we begin, I'd like you to recall that in the last chapter, we discussed decision rules, namely the minimum distance rule and the maximum likelihood rule, and we also defined associated R error correcting codes. But we did not learn how to systematically create error correcting codes, how to test received strings to see if they're code words, or how to decode received strings. So we're hoping that we will be able to use this material on linear codes to do these things. So in the last video, we learned what a linear code is and how to create code words by taking linear combinations of columns of a matrix. So in today's video, what we're going to do is to explore error correction properties of linear codes. One thing that's easier to do in linear codes than in other types of codes is measure distance. So here on this slide, we have a theorem about measuring distance in linear codes. And the theorem involves this word weight. So the weight of a string x in f2n is just the number of ones that's in x. So for instance, if, if x were equal to 0, 1, 0, 0, 1, then the weight of x would be 2 because there are 2 ones in x. Now, you might observe that we can express weight in terms of the Hamming distance, right? So the weight of a string is really the distance between the string and the zero string. Okay, another thing about Hamming distance in F2n that I want to point out is that, if you look at the distance between any two strings x and y, and then you add string z to both x and y, it does not change the Hamming distance. Right? X and y will differ in the same slots that x plus z and y plus z will differ in. And then finally, a little fact about addition in F2n. If I take any string and add it to itself, I get this string of zeros. All right, so now to the theorem. The theorem tells us that if we have a linear code, then in order to measure delta, which is the minimum distance between two distinct code words, all we have to do is find the minimum weight of a non-zero code word. So let's see how that plays out. Well, delta is the minimum distance between non-zero code words, so it must be achieved by some pair of code words. So let's let C and C prime be in our code C, with delta being equal to the Hamming distance between C and C prime. Then delta is equal to the distance between C plus C and C plus C prime. Right? So remember, all we're doing is we're taking this initial distance here and we're adding C to both objects, to both strings. But remember, C plus C is 0. That's the 0 string. But this is just the weight of C plus C prime. So that says that our delta is the weight of some non-zero code word. Now, C plus C prime must be non-zero because C and C prime are not equal. right? Remember, to measure delta, C and C prime must be distinct, and that forces the sum C plus C prime to be non-zero. All right, so good. We have delta being the weight of a non-zero code word. And frankly, if there were some non-zero code word with a smaller weight, then the delta in turn would have to be smaller. And so this ends up proving the theorem. Here we're going to do an example in which we apply the previous theorem. So here we have a three-dimensional linear code determined by this matrix E, and we're supposed to determine what the code words are and then find the value of delta for this code. So for the code words, remember, we are to take all linear combinations of the columns of E. And what that means is that we're going to think about all of the possible matrix products of this matrix E by vectors x1, x2, x3 in F23. So what we wind up with when we make this product is it's x1 times the first column of E plus x2 times the second column of E plus x3 times the third column of E. And when you do that, what you wind up with is x1, x2, x3. And then in the last two bits, we get x2 plus x3. And then finally, x1 plus x2. So now all we need to do is replace x1, x2, and x3 by zeros and ones to get all of these vectors with all of these members of F25 that are code words. Okay, so if x1, x2, and x3 are all zeros, then we wind up with this as our first code word. If we start with 0, 0, 1, then we wind up with this code word. If we have 0, 1, 0 for x1, x2, x3, then we get this code word. How about 0, 1, 1 for x1, x2, x3? Then this becomes this code word. And then moving on, 1, 0, 0, 0, 1, and then 1, 0, 1 for x1, x2, x3, and we should get 1, 1 to fill out the last two bits, and then 1, 1, 0 gives us a 1 and a 0 for the last two bits. And then finally, x1, x2, x3 being all ones is going to result in zeros in the last two bits. So these 8 strings are our code words. And down below each of them, we can write the weight of the code word. Okay, so the weight of the 0 word is just 0. The weight of the next code word, remember we count the number of ones, so there are 2 ones there. There are 3 of them there, 3 of them here, 2 of them there, and then 4 of them here, and then finally 3 ones in the last 2 code words. Now remember that delta, according to our previous theorem, right, instead of having to compare every single pair of non-zero code words, which is, on the order of, 50 or 60 code pairs to consider, all we need to do is look at the weights of the 7 non-zero code words. So the smallest weight that we see anywhere is 2, right? In fact, that occurs twice here. And therefore, according to the previous theorem, delta is equal to 2. Right, so once again, the advantage in this is that instead of having to compare every single pair of non-zero code words, all we have to do is look at each single code word individually and look at its weight. The smallest one of those weights will be delta. Now, one thing we notice from this, delta is equal to 2, which means that this code will not even correct a single error, right? Remember, delta needs to be 3 or larger to be able to correct one error. Here again, we're going to consider the code that we talked about on the previous slide. Right, so remember that code is formed by looking at the linear combinations of the columns of this matrix E. So what we're going to do is we're going to form a new matrix by taking this matrix A from the previous code. We're going to put it here and put it next to the identity matrix I2. And then we're going to compute the products H times C for every code word, and we're going to see what happens with that. Okay, so first of all, let's remind ourselves what E looked like from the previous slide. Okay, so remember that was a 3-dimensional code, meaning we had the identity matrix on top. And then down below, we had the matrix A that looked like this. And so this is E. Which is the 3 by 3 identity matrix, and then A down below, which is a 2 by 3 matrix. So this doohickey right here, that is the matrix A. Now for H, what are we going to do? We're going to take this matrix A, and we're going to set it next now to the 2 by 2 identity matrix. In fact, that's the only identity matrix we could set it next to in order to fill out a matrix. And then what we're going to do is multiply this matrix by every single code word that we got on the previous slide. Now look, there were a lot of code words there, so we're just going to do a few of them here, and hopefully we'll get the point. Right, so first let's multiply by the code word 0, 0, 1, 1, 0. Now you might remember from the previous slide that that is indeed a code word. Now what do we get? Well, what that means is we're taking 0 times the first column plus 0 times the second column plus 1 times the third column. So we have 1 times the third column, 1 times the fourth column, and then we have 0 times the fifth column. Now what does that do? Well, essentially we're just asking ourselves to add the third and the fourth column of H together, and when we do that, the outcome is the 0 string. Okay. All right, well, if you didn't like that, let's try another one. So let's take another code word here and see if we get a different result. So you might remember from the previous slide that this was also a code word. 1, 1, 0, 1, 0. Okay, that was also a code word. And now when we multiply the matrix times that vector, What are we doing? Well, apparently we're taking 1 times the first column plus 1 times the second column, 0 times the third column, 1 times the fourth column, and 0 times the fifth column. So we're being asked to add the first, second, and fourth columns of the matrix H. And when we do that, in the top entry, we get 0 plus 1 plus 1, which is 0. And in the bottom entry, we get 1 plus 1 plus 0, which is again 0. So you might take a moment now, maybe pause the video, go back to the previous slide, pick some more code words, and multiply on the left by H. Every single time you do that, you should wind up with the string 0, 0. Okay, so it turns out that that is not a fluke. Okay, so the previous example illustrates this theorem. It says that, if we have a code determined by a matrix E, like this, if we then form the new matrix H in this way by taking the matrix A, moving it here and placing it alongside the n minus k by n minus k identity matrix, then a string is going to be a code word if and only if H times C is the 0 string. So this is a neat theorem. It tells us that a very simple way to determine whether a string is a code word. We just put it next to H and multiply. If the result is 0, we're golden. If the result is non-zero, then the string is not a code word. So for that reason, the matrix H in the theorem is called a check matrix for our code. All right, so let's prove the theorem. So it's an if and only if statement. That means it requires 2 proofs, a forward direction and a rearward direction. So for the forward direction, we suppose C is a code word, and we're going to show that H times C must be 0. So if C is a code word, then we know that C is equal to E times X for some X in F2K. And when we take E times X, that is just the vector IK times X, and then AX on the bottom. Remember, the identity matrix times X is just X itself. So this is just X, and then AX on the bottom. So now let's take H times C. Well, that is apparently A, and then the identity matrix next to it of size n minus k. And then we're multiplying that by the vector X, AX. And when we do that, we're going to get AX plus the identity matrix of size n minus k times AX. But that's just AX plus AX. Now remember from a couple of slides ago that if you take any string and you add it to itself in this vector space, you're going to get 0. So that's exactly what we wanted to have happen, right? H times C for any code word is equal to 0. All right, very well. So now let's go the other direction. So we're going to prove now that if we have a string and its product with H is equal to 0, then that string must have been a code word to begin with. So suppose H times C equals 0. Now we can think of C as having two parts. A first part of length k, and then a second part of length k n minus k. And I'm going to label those two parts C1 and C2. So C1 is of length k, and C2 is of length n minus k. So now we've got that so now we have this. So that's equal to the 0 string. And so that says that A times C1 plus C2 is equal to 0, which says that A times C1 is equal to minus C2, but in this vector space over F2, the negative of anything is itself. So this says that AC1 is equal to C2. Thus, this C is C1 atop A times C1. But guess what? That's the same as E times C1. So this C is indeed a code word, right? Because it's a linear combination of the columns of E. So the check matrix for a code is an extremely useful gadget. In fact, that's illustrated here by this theorem that says if you've got a linear code and you want to know whether it's a one-error correcting code, all you have to do is form the check matrix, and then if no column of the check matrix is the 0 vector and no two columns of H are identical, then you know immediately that the code is a one-error correcting code. So that's a very fast process for testing whether a code corrects one error. So let's go ahead and prove this theorem, or at least one direction of this theorem. So in order to do this part of the proof, we need a little bit of notation. So first of all, we're going to introduce this E sub I, which is the ith elementary vector. It is a string of length n, where it has a 1 in the ith slot. And it has zeros elsewhere. Meanwhile, we're going to let H sub I be equal to the ith column of our check matrix H, capital H. Okay, one thing I want you to notice here is that if you now take your check matrix and you multiply by this ith elementary vector E sub I, then that yields exactly the ith column of H. So again, just to make sure we understand each other, this elementary vector, say E2 in say strings of length 5, that would be a string of length 5 that has a 1 in the second position and zeros everywhere else. Okay, so now we're going to prove the forward direction of this theorem. And we're going to prove this by contradiction. So we suppose that C is an error-correcting code. So it's a one error correcting code. With a check matrix So check matrix H. All right. Let's now suppose for a contradiction that there is a column of H that's the zero vector. Okay, so if it's true, so if HI is the zero vector for some I, then when I take H times EI, I'm going to get little h sub I, but that's the zero vector. Now what that tells me, because capital H is a check matrix, that says that E sub I is a code word. But there's a problem with this, right? If you look at the weight of E sub I, remember the weight counts the number of ones in a string, so the weight of this E sub I is equal to 1. But that contradicts the fact that delta, the minimum distance between two distinct code words, must be 3 or larger. Right? Remember, earlier on we had a theorem that said that the minimum distance between two code words in a linear code is the smallest weight, or the minimum weight of a non-zero code word. So here, that minimum weight has to be at least 3, and it's not that in this situation. Okay, so we see that if a column of H is the zero vector, then bad things happen. Now let's suppose we have two columns of H that are identical, right? So let's now suppose H sub I is equal to H sub J. For some indices, unequal indices I and J. Then if we take capital H, our check matrix, and apply it to E sub I plus E sub J, then that will be little h sub I plus little h sub j. But remember that if you have h sub I and h sub j are equal, and that means that, remember, in this vector space, if you have two equal vectors and you add them together, you get the zero vector. So that means that E sub I plus E sub j is a code word. But again, the weight of E sub I plus E sub j is equal to 2, right? That's equal to 2. And that is a contradiction. That contradicts that, again, that delta needs to be bigger than or equal to 3. So that shows that no two columns of H can be identical, and that proves the theorem. Okay, let's use theorem 4 to produce, if possible, check matrices for linear codes satisfying certain parameter values. So here in each of A, B, and C, we see these parameters n, k, delta. So n means that our code is going to live within strings of length n. K is the dimension of the code. So remember, the code itself is not all of the strings f2n. It's some subspace of f2n of dimension k. So k is the dimension of our code. And then delta, remember, is our minimum distance between two distinct code words. Now I realize that the slide says that we are to have delta equaling 3, which would certainly give us a 1 error correcting code. But really what we mean here is that delta is bigger than or equal to 3. So contrary to what's written on the slide, delta doesn't have to be exactly 3. All it needs to be is something that's bigger than or equal to 3. Okay, so that's what we're going to try and do. Produce a k-dimensional code within f2n where delta is bigger than or equal to 3. All right, so let's just start doing this, right? So in H, we know that, or in part A, we know that our check matrix H is going to look something like this. So it's I sub n minus k. N minus k in this instance is equal to 3. So it's going to be A comma I3. Now, how big is A? Well, remember that this matrix H has n columns. So A is going to be 3 by 5 minus 3. Right, it needs to have those dimensions in order for the matrix H to have 5 columns total. All right, so that means that this matrix is going to look something like this. So I3, remember, is the 3 by 3 identity matrix. And now in order to fill in this remainder of this check matrix in a desirable way, I need to have 2 columns, one here and one there. And remember from Theorem 4 that if this is going to be a check matrix for a 1 error correcting code, that is if we want delta to be bigger than or equal to 3, then these 2 columns have to both be non-zero, and they can't repeat each other or repeat anything else that we've written down in terms of columns. So I can't write a column that has 1 non-zero entry and 2 zero entries because those have already all been written down. And I can't write a column that has all zeros because then that would be a 0 vector as a column, and that's forbidden. So what I want to do is write down column vectors that have 2 1s. And I can do it, right? There it is. There's my check matrix. For an error correcting code, a 2-dimensional error correcting code in F2.5. Okay, so let's try the same thing for part B. There, n is 4 and k is 2. So what is H, our proposed check matrix, going to look like? Well, there, n minus k, in part B, n minus k is equal to 2. And so I2 goes over here on the right. And there are 4 columns. Because n equals 4, there's 4 columns here in this matrix total. And so we know that this matrix is going to look something like this. And now to fill it out, if I'm going to be able to produce a check matrix for a 1 error correcting code, I've got to put 2 vectors there that are both non-zero and don't repeat anything we already have. Right, so the only thing I can put here, say, that is non-zero and won't repeat what we've already got is 1, 1. But now, when I try and fill this last column, there's nothing, I have no choice there about what to put. I can't put anything there. And so what we conclude is that no such code exists. Right, so there's no linear, two-dimensional linear code in F2.4 that can correct one error. The code words would just wind up being too close together. Okay, and now in item C, we have a rather famous, we're going to develop a rather famous code called a Hamming code that we'll talk about in the next video. But for now, we don't necessarily need to worry about that. So I'm going to go ahead and get rid of our solution to part B so that we have a bit of room for part C. Okay, so they're building again on what we did in part A. Well, what is our proposed check matrix going to look like? It'll be A, and then n minus k in this instance is equal again to 3. So we're going to again have the 3 by 3 identity matrix over on the right, just like we did in the first example. So this is going to be an A. And then over here we'll have 1, 0, 0, 0, 1, 0, 0, 0, 1. Now, unlike part A, where the entire matrix H had 5 columns, this time the entire matrix H is going to have 7 columns. So that means that I need 4 more columns to fill out A. So that means I need 4 more non-zero vectors in order to make this work that don't repeat anything. Right? So what if I tried doing this? Well, I take 1, 1, 1, that's non-zero. About 1, 1, 0. 1, 0, 1, and 1, 1, 0. And then I put that together with my existing columns that I had from the identity matrix. And that does what I want it to do, right? They're all non-zero, and they don't repeat. And in some sense, this is the best we can possibly do with with the n minus k equaling 3, because this list of vectors is the entire set of non-zero vectors of length 3. So in some sense, this is an optimal code. And in fact, it's called a perfect code. And we'll see why that is in a future video. At any rate, all we need to know is that this is a 4-dimensional, 1-error correcting code inside of F2.7. Okay, now there's a more general version of Theorem 4. Right? Theorem 4 told us that if you're looking at a check matrix for a 1-error correcting code, you can't have any columns being identically 0, and you can't have any 2 columns being repeats of each other. So those of you who've had some linear algebra, this theorem statement, this generalized theorem statement will probably make some sense to you. So let's suppose we have a linear code C with check matrix H. Then C is an R error correcting code, not just 1 error correcting code, but an R error correcting code if and only if every set of 2R columns chosen from H is linearly independent over F2. We've now learned a little bit about how to produce linear error correcting codes, but there's still the problem about what to do with strings that we receive in transmission. In particular, if we receive a string, we want to apply a decision rule, like the minimum distance rule, to assign that received string to a code word. So this is still a hard problem, even with linear codes, but there are some shortcuts for linear codes. In particular, we have this theorem 5, which applies to one-error correcting codes. So let's suppose we've got a one-error correcting linear code with a check matrix H. And suppose at most one error is made in transmitting code word V. And let's suppose that Z is the received word. Then Z is going to be V if and only if H times Z is equal to 0. And V is going to be Z plus the ith elementary vector, which we introduced on a previous slide, if and only if H times Z is the ith column of H, which again we introduced on a previous slide. Okay, so let's take a look at these items A and B. Well, let's suppose H times Z is equal to 0. That means that Z is a code word. Now, Z then must be equal to V, because if Z were not equal to V, remember, only at most one error is made in transmission. So that would mean the distance between code words Z and V would be equal to 1. But that is impossible because our code is one error correcting. And that means that the minimum distance between distinct code words must be 3 or larger. Therefore, if H times Z is equal to 0, then Z must be equal to V. Okay, and likewise, if Z is equal to V, then Z is a code word, and H times Z then is automatically 0. So now let's suppose that H times Z is equal to the ith column of H. Well, if that's true, then if you take H times Z plus EI, then you get HI, because that is H times Z, and then you also get H times E sub I, which again is the ith column of H. And if you add a vector to itself over F2, you get the 0 vector. So that means that Z plus EI is a code word. And remember, Z is obtained from V from at most 1 bit error. So that means that the distance between Z and Z plus EI and V is at most 2. And they're both code words. Well, remember, the minimum distance between code words is 3 or larger. And so that means the only way that the distance between Z plus EI and V can be less than or equal to 2 is if they're equal words to begin with. And likewise, if you assume V is equal to Z plus EI, and you apply H to these both sides, you'll wind up with this property for that H times Z must be the ith column of H. Okay, so that previous theorem really makes correcting errors in transmission pretty easy for one error correcting codes, as long as we're sure that at most one error has been made in transmission. So here we've got this one error correcting code, and in fact, this is that this check matrix H probably looks familiar. This is, the 4-dimensional code in F27. And here we've got these strings Z1, Z2, and Z3 that we've received in transmission with at most one error. And we want to see, how we should correct these. So the previous theorem tells us to first take H times each of these. So we're going to take h times z1. And when we do that, h times z1, that is, so z1 is 1, 1, 1, 0, 1, 1, 0. So that means we're going to take 1 times this column, 1 times that column, 1 times that column, 0 times this column, the column of all ones, 1 times this column, and 1 times that column. So we're going to add together all of the columns that have dots above them currently. And when we do that, what do we get? Well, in the top component, what do we get? We get 1 plus 1 plus 0 plus 1 plus 0, which in total is a 1. And then in the next component, we get 0 plus 1 plus 1, that's 0, plus 0 plus another 1, which is a 1. And then finally, we get a 1 plus 0 plus a 1 plus 0, right? A 1 plus 0 plus a 1 plus 0 plus 0. So that is 0. Okay, now I'm going to look at this. And which column of H is that? Well, that's the second column. It's this one right there. So that's H2. And so what that means is that the original code word, if we apply the previous theorem, the original code word must be Z1 plus E2. So how do we obtain that sum of Z1 plus E2? Remember, E2 is the string that has a 1 in the second slot and zeros elsewhere. So that means the result is obtained by just changing the second slot of Z1 and nothing else. Okay, so that's the correct, that was the intended code word, and we're sure of it. All right, so maybe you want to pause the video and try and do the same thing for Z2. All right, so let's erase a little bit of this stuff. All right, now I'm assuming that you've gone and tried to do this. Right, so we're taking H times Z2, which means because Z2 is 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, we will be adding together the second, third, fifth, and seventh columns of H. And that's going to give a vector with 3 components. So in the top, I take 1 plus 0 plus 1 plus 0, which is 0. It's very good. And then we have 1 plus 1, which is 0, plus another 0, plus another 0. So that's 0. And now in the bottom, we have a 0 plus 1, plus a 0 plus a 1, and that's 0. So that means that V is just dead on equal to Z2. That means that no mistake was made. Okay, and I think I'll let you all handle Z3. Okay, so there's a more generally applicable method for applying the minimum distance rule in linear codes. And that method is called syndrome decoding. So we'll need a little bit of background before we can introduce the process of syndrome decoding. So we're going to let C be a linear code with check matrix H, and we're going to let W just be an arbitrary string in F2N. Then the coset of C with representative W is all of the translates of these code words by W. So you can imagine F2N as maybe being this rectangle, So that's F2N. So it's everything inside there. And then our code C sits in here, maybe as this line. And then W plus C is what you get when you add W to every single code word. And so that's going to be maybe something like this up here, W plus C. So you would imagine that all of these translates would fill out the entirety of F2N. Okay, so that's what a coset is. It's a sort of a parallel translate of the code words, all the code words in C. And then we have this idea of a syndrome. So a syndrome is obtained when you take your string W and you multiply by H on the left. Okay. Now, when the syndrome is 0, the 0 vector, that happens exactly when W is a code word. Okay, so we have this little note at the bottom that says that X and Y will have identical syndrome exactly when X and Y lie in the same coset of C. So let's see why that's the case. So let's suppose that X is some string W plus V1, where V1 is a code word, and Y is W plus V2, where V2 is a code word, right? Then both X and Y are living in the coset W plus C. Now to get the syndrome for X and Y, we apply H to both of them. So H times X is H times W plus V1. But that is equal to H of W plus H of V1. But remember, V1 is a code word, and so H times V1 is going to be 0. So this is just H of W. But remember, V2 is also a code word. So H times V2 is 0. Right, I'm just adding that on there because H times V2 is 0. And then again, that's H of W plus V2, which is H of Y. Right, so H of X and H of Y are identical, which is tantamount to saying they have the same syndrome. So we'll test our knowledge of this new terminology by doing an example. So here we have a linear code contained in strings of length 4 with this check matrix H. And there are several things that we want to do. We're going to list the members of the code, or that is list all of the code words. We're going to list the distinct cosets of our code. And then within each coset, we're going to identify an element of minimum weight. So that's an element of minimum weight called a coset leader. And then we're going to find the syndrome associated to each coset. All right, so first for listing the elements of our code, well, here we're only given the check matrix. And so you might be wondering, how in the world do we generate these code words? So remember, the check matrix is broken up into 2 parts. So there's the A, and then there's the identity matrix. So remember the relationship between the check matrix H and sort of the generation matrix E. What we do is we take that A, and sit it down here, and then it sits below an identity matrix. So remember, A here is this 1, 1, 1, 0, and the question is, well, what identity matrix can you put above it? And the only one that will fit is the 2 by 2 identity matrix. So this is going to be a 2-dimensional code in C4. And so how do we get the code words? Well, C is just the collection of all things of the form E times x1, x2. Such that x1, x2 is in F2, 2. And what's that going to look like? Well, if you take E times x1 comma x2, that's going to be, let's see, it'll be things that look like x1, x2, and then down below it'll be x1 plus x2, and then just x1 again. So it's the set of all those things. Such that the string x1, x2 is in F2, 2. And now what does that really mean? Well, let's list all those things. So if x1 and x2 are both 0, then what we get is just the string of all zeros, 4 of them. And here I'm writing them horizontally now. If x1 is 0 and x2 is 1, then we get 0, 1. 1, 0. Now, if x1 is 1 and x2 is 0, we get 1, 0, and then 1, 1. And then finally, when x1 and x2 are both 1s, we're going to get 1, 1, 0, 1. Okay, so that's part A. Those are our code words. And again, when you're given a check matrix, you identify this A first. You then set it underneath the appropriately sized identity matrix. Then you have this sort of generating matrix E that you can use, take linear combinations of the columns to get the code words. Okay, so now for the rest of what we're going to do, I'm just going to retain the list of code words. So let me go ahead and do that, erase some of this work so that we will have more room later for other things. Okay, so let's remember now what our code is. C consists of 0, 0, 0, 0, and then 0, 1, 1, 0, 1, 0, 1, 1, and then finally 1, 1, 0, 1. Okay, so now we can feel free to erase this last bit here, now that we have transcribed it. Okay, now we're supposed to list the cosets of C. How do we do that? Well, remember the cosets of C are translates of C, so I need to take some arbitrary string and add it to C. Well, the easiest thing I can do is take just the string of all zeros and add it to C. And guess what? If I take the string of all zeros and I add it to every single code word, then that's just the code to begin with, right? So that's just, I'm just going to list the coset elements underneath here. It's just what we started with, right? So it seems like we have done nothing, but actually this is a coset of C. It's just sort of the trivial coset of C. Okay, now what else can we do? Well, let's think of something else that we could add to everything in C. And my suggestion would be to start with things that are sort of easy, that would have a lot of zeros and not many ones. So how about like 0, 0, 0, 1 plus C. So now I'm going to add everything 0, 0, 0, 1 to everything that's in C. So if I add this 0, 0, 0, 1 to 0, 0, 0, 0, I just get that. And then when I add 0, 0, 0, 1 to the next code word, I get this, and then this, and then finally this. Okay, now let's keep in mind that we should be adding sort of things to C that are fairly simple. So what about something like 0, 0, 1, 0? Okay, so I get 0, 0, 1, 0. Now I'll add that to everything else that's a code word. And let's see here. Okay, now the next thing we might try to do is this. Now, if we try to do this, we're going to be disappointed because the coset that we're going to wind up with is going to be one that we've already got. And the reason I know that is because this 0, 1, 0, 0 already occurs in this coset. Now, one little fact about cosets is that they either agree or they're completely disjoint. Okay, so I know that 0, 1, 0, 0 here, that's going to be in this, would be in this coset, but it's also in that coset, this third coset, which means that the two cosets are not disjoint, which means they would be exactly equal, right? So I want to pick something else besides that translate. So let's pick something else, maybe small here that we don't already have. How about 1, 0, 0, 0? So I check it, all my other cosets, and I don't see that I've got that yet. So let's try this. So now I get 1, 1, 1, 0. So I'm adding this 1, 0, 0, 0 to every code word. Let's see. 0, no, hold on. I'm going to get 0, 0, 1, 1. And then finally 0, 1, 0, 1. All right, now at this point, I could continue to try to add cosets, but I'm never going to be able to add any more of them. And the reason I know that is because I know that there are only 16 words total of length 4, and I've accounted for all 16 of them in these cosets, right? I've got all of them. And so any other coset that I produce will be a replication of what I've already got. Okay, so those are the distinct cosets of C. And then within each coset, we're to identify an element of minimal weight called a coset leader. So it's up to us to identify those things. So let's do that. Well, and actually we want to identify, right. So here in the code itself, the element of minimum weight would be this doohickey, right? Just all zeros. The weight of that is 0. Within our second coset, 0, 0, 0, 1 is of minimal weight. Now, in our third coset, we have two choices, right? We've got 0, 0, 1, 0, and we've got 0, 1, 0, 0. So either one of those could be selected, and why don't we stick, for no particular reason, with the one that's already been circled. And then in our last coset, again, there's no choice. This is the one of minimum weight. So those will be the coset leaders. Right? So those are the coset leaders. All right, and now let's go ahead and find the syndromes for each coset. Now you might be thinking, well, wait a minute. A syndrome is something applied to a string, not a coset. Remember, all of the elements in any given coset have the same syndrome. Okay, so I'm going to make a little table here of coset leaders and their corresponding syndromes. All right, so our first coset leader is 0, 0, 0, 0. And remember, the syndrome is obtained by multiplying the coset leader by the check matrix H. Well, since this is a code word, I know that the syndrome is going to be 0, 0. Remember that outcome, when you take H times any object, the outcome is going to be some string of length 2, right? Because the columns of H are of length 2. So our syndrome is going to be a string of length 2. All right, so our next coset leader is 0, 0, 0, 1. And if I multiply that by H, what I'm doing is I'm just picking off the last column of H. So that's going to be 0, 1. And now we've got 0, 1, 0, 0 as the next coset leader, and when we apply H to that, we're picking off the second column of H, and that's 1, 0. And then finally, we have 1, 0, 0, 0 as a coset leader. When we multiply H by that, we're picking off the first column, which is of H, which is 1, 1. So those are the coset leaders and their syndromes. Okay, so now that we know just enough about syndromes and cosets, we're ready to present the method of syndrome decoding for a linear code C with check matrix H. So in other words, what we're trying to do is apply the minimum distance rule, okay? All right, so we receive a word, right? We're there wearing our green visor, sitting in a room, and we receive a word Z, and what we want to do is apply the minimum distance rule to Z in some sensible way. So the first thing we do is we compute the syndrome corresponding to Z. That is, we multiply by H. So then that's step 1. Step 2 is we're going to find a coset leader F that corresponds to this syndrome S. In other words, we're going to find a string F where when we take H times F, we also get S. And there's this, under the proviso here, that F is a minimum weight object that does this, okay? So the next and final step is we compute V, which is Z plus F. So first of all, I submit to you that Z plus F, namely this V, is a code word. And the reason for that is that if you take H times V, then that's the same as H times Z plus H times F. But Z and F both have the same syndrome, namely S. And when you take any vector and add it to itself over F2, you get the 0 vector. So H times V equals 0. And that means that V must be a code word. And further, V is as close as possible to Z because F, this F that we chose, is of minimum weight that would make this happen. All right, so let's see how this works. So let's consider the code we had in the previous example on the previous slide. And we're going to use syndrome decoding to apply the minimum distance rule to this received word. All right, so we just follow our steps, 1, 2, 3, right? So I take, first of all, the check matrix times Z, and we have to remember what the check matrix was, right? So from the previous slide, it's 1, 1, 1, 0, 1, 0, 0, 1, and we apply that to our vector Z, which is 0, 1, 0, 1. So apparently we will be adding the second and fourth columns of of H together, and that's going to give us 1, 1. So that's our syndrome. Now, remember that we had this syndrome lookup table that we had on the previous slide. So we had these coset leaders and syndromes down here. And I'll just remind you what that table looked like, right? So the syndrome corresponding to leader 0, 0, 0, 0 was just 0, just 0, 0. And then 0, 0, 0, 1 was 0, 1. And then 0, 1, 0, 0, the syndrome for that was 1, 0. And then finally, for 1, 0, 0, 0, the syndrome was 1, 1. And there we've hit the jackpot, right? So I'm looking for the coset leader that corresponds to the syndrome 1, 1. So there it is. There's my coset leader. And so to apply the minimum distance rule, what I'm now going to do is compute V, which is Z plus F. Z now is 0, 1, 0, 1. And F, our coset leader, is 1, 0, 0, 0. And when we make that sum, we get 1, 1, 0, 1. So that is the code. That is a code word that is as close as possible to Z.